Anyone not turned in homework 2? I think I have everyone's homework 2, right?
Homework 2?
Yeah.
Why would ChatGPT on this?
On a homework 3?
Yeah.
Yeah. Yeah, it's kind of fun though, right? Useful or not useful?
It's interesting because it's like talking to a different person, it can generate response.
Yeah.
It's like this is the same guy who wrote the last.
Well, there's some people who are interested in breaking ChatGPT, like finding out what the limits are. I forget what the Reddit group is, but they like figure out how to teach it to turn off its like safe filters and like reveal an underneath personality. Pretty weird. Yeah.
Saw a video recently where like they were able to make ChatGPT say 2 + 2 is equal to 5.
Yeah.
Oh,
Yeah.
I like that.
1, 2, 3, 4, 5, 6. I think we're pretty close, so we'll just start right now because it's 4 o'clock. So I think we're sending up email right now. It's really cloudy, so we won't be going up to the observatory. So instead we'll do spectroscopies, which are all of these little lamps around us. Kind of fun if you've never seen a spectral lamp before. And these are going to have gases inside of them. Please do not touch them. Please do not turn them on. They are high voltage machines. So if you open it and you put your finger in, bye-bye. Right? Yeah, you pull the bulb out, you put your finger in. And I'm not supposed to let you die in the lab. That's one of the rules. So we're not going to do that. We'll play with those. We'll turn them on and we'll look at them in the second part of the class. But before we do that, we're going to talk about light today. And light is really important because it's our dominant sense. All the rest of our senses depend on light. And in fact, our brain prefers light to any other sense. So if you want to see something fun tonight, look up something called the McGurk effect, which is the what? MCGURK. What it is that if I say the word Bob or the word Bob, depending on what you see my lips doing, your brain will change the sound. There's a lot of brain induced optical illusions. We won't talk about them in any detail, but we will talk about how light gives us most of the information that we're going to get about the rest of the universe. So for example, we can fly to Mars, but you could never fly to the nearest sun, star. And so how do we get information about that? And so just to start for today, we're going to start with this little piece here. Just want to clarify a few things when we're talking about the homework. So for this first part here, recall that it says define the following terms in your own words. So while I encourage you to use ChatGPT and to use the textbook and use Google to determine what these things mean, I want to know what they mean to you. And the reason that I care about that is because I want it to be a reflection of your understanding in the class. You'll notice that I'm fairly specific about the words that I use. So if we're talking different languages, like for example, I saw the response a lot on the ellipticity. People were saying, oh, it's like an ellipse. That's not a definition, right? So if I say something is fiery and you say, oh, that means it has fire on it. You see how you've not really defined it, but you didn't tell me what a fire was. Similarly, if you look at ellipticity and you say, well, it's oval or it's egg-shaped, that's actually incorrect. Because an oval is a very specific shape, however, like an egg, and no orbit is like that. Because an egg looks like this, fatter on the bottom, and an ellipse isn't fatter on the bottom, it's just squished, like someone sat on a circle. Okay?
So is that a good example of what we could write?
Yeah, you can say squish circle. Squish circle is one of my favorite definitions. And feel free, like when I say stuff in here that are sort of like weird, outlandish definitions, you can use those, right? So you said that, you throw it back in my face. I'm totally okay with that, right? But my idea is I want to just like understand what you understand, okay? And I want to make sure that the homework's helpful for everyone. So if people say in general, oh, I really hated this section, it feels like busy work, you can give me that feedback. I'm a human being, and then I can adjust it. Okay? Questions about homework 2, 3? Okay, I'll release homework 4 tonight. I realize that I'm way behind on getting you your graded homework, and I apologize for that. Thank you for your patience. Okay. So let's start with light. Oops, not vorticity dynamics. My bad. Uh-oh, where'd it go? Ah. Okay. All right. And I didn't update them. Well, this is very similar slides. Pretend like that says ASTR 2300. Can you turn off half the lights, Stephen?
No.
One more. Yeah, there we go. Okay, what am I looking at?
Light spectrum.
Light spectrum, light spectrum. Wavelength, absorption.
Hello.
Colors,
Rainbow.
rainbow. I like rainbow.
Visible wavelengths.
Visible wavelengths. Good. Okay, so in fact, we're seeing what we're seeing, right? Good.
Yeah.
Anyone with color blindness? Yeah, okay. So which part of this is very similar to the other parts for you?
I have protanopia, so any like dark reds, greens, browns come the same.
So this looks the same as this?
Pretty close.
Yeah. Yeah. Okay, so this goes from purple on this side through blue, green, yellow, orange, red. And what are the dark lines? Gaps? Why are there gaps in this?
Where light is absorbed.
That is where light is absorbed. So darkness, for example, on this side of the room is the absence of light, and light is the presence of light, right? So interestingly enough, black really isn't a color in the way that we traditionally think of color. It's the absence of color. What's all the colors put together?
White.
White. Okay. All right. Good. So that's the basics of light. What is this?
It's not.
That's the sky. Very good. This is a picture of the past couple, maybe like a week or so. Every single day, we were watching. Oops, I'm gonna trip and kill myself. This is well, I didn't on purpose. There's a cord here. This is Venus getting closer to Jupiter. So did you see when it was like this? And people were calling the sheriff's department, there's aliens.
And they were kissing. Very cringe.
Well, yes, that's very cringe, and also they're not kissing, and why is that?
Because they're
So
not making.
not next week.
They're very far from each other, right? This is cool. This is like the moon came in for its selfie really quick. And what's another cool thing you see here?
It's like a triangle.
There's a color change. There's a dramatic color change, right? So every night at the same time, you actually don't get the same color sky, right? So this color of the sky is changing from night to night, and the colors are telling you about something in the atmosphere. We'll talk about that when we talk about atmospheres as a whole. Okay, so we're going to talk about all of light. You ready? We're going to do it really quickly, and then we're going to get into climates. Okay. What's light? Electromagnetic waves. Anything else? Particles? Wave particles? Photons? Okay, so these are all words for the same phenomenon. Okay, so the particle of light, which is a weird thing about quantum mechanics, is a piece called a photon, but it behaves like a wave. So it behaves both like a wave and a particle. Weird, but that's because we don't live on the scale of light. Okay. What is light? When we think about the word light, we tend to think about visible light, and that is not a large enough definition. So in fact, if I were a snake, I would see you all, but I'd see you in infrared. So that's the heat that you're giving off. You are radiating light. We just can't see it. Our eyes are not attuned for that. If I were a butterfly and I were flying around outside, the flowers have special patterns on them that are only visible in ultraviolet light. And you can't see them, but a butterfly can. It says, the nectar is right here, come eat the nectar. And so you fly down and you eat the nectar. Okay. So light is a very broad definition for all electromagnetic rays. And we'll talk about all of them in a few minutes. So we are going to ask the question, how can we tell what a star or planet is made of? if we can't go there? We're gonna answer that. And then why can someone get a tan from the sun, but not the oven? That's a good question, right? There's a corollary to this, right? So like you put your chicken into the oven, the skin burns, everything is bad, right?
It's good.
It's good, it's real good. But you don't get a sunburn by cooking your chicken, right? So we want to understand why that happens. And importantly, let's do a quick question here. Microwaves, right? Very contentious. If you grew up in the 90s, your mom maybe said, oh, they're not safe. Microwaves safe or dangerous? Raise your hand if they're dangerous. Raise your hand if they're safe. Okay, interesting. Cell phones or cell phone towers, raise your hand if they're safe to your brain. Dangerous if you're left-handed? Oh, interesting. Okay, we're gonna find out. 5G. Oh yeah. So 5G, is that are those maps of COVID related? No. That's what we call coincidence. Very good. Okay, so what are some different types of light? I've given you some examples already. Give me a type of light.
LED.
Sorry. That is a correct answer, but when we're talking about electromagnetic waves, what types of electromagnetic waves are there? UV, very good.
Gamma.
Ultraviolet is UV. Gamma, okay, good. Beta is not quite, that's a tricky one. Infrared, we'll get to beta later. Radio, X-ray, micro. You're only missing like the one that we use. Visible, okay, good. All right, so in fact, here's all the ones that you just mentioned. Okay. People had an X-ray before?
Yeah.
Good. Should you get a lot of those?
No.
No. What about this one? Gamma? What does gamma do?
Goes right through you.
It's radiation.
It's what creates the Hulk, right? We all know that from the very common documentary on okay. So we talked about this briefly before. White light is all colors put together in your brain. And so, for example, you can separate it with this thing called a prism. And we will do some separation today with these diffraction gratings. These are like little baby prisms, so to speak. Take them up to your eye. If you ever use a ray glass, that's what this is. Okay. All right. Here's the electromagnetic spectrum, and we're going to break it down. So this is this that we can see right here in the visible. And what you're looking at here is the wavelength. Okay. So we're going to define what the wavelength means in a few seconds. But this would be short wavelengths, close together, and this would be long wavelengths, far apart. So let's look at the size scale here. Visible light is about the size of bacteria. It's pretty surprising. Radio waves can be as large as a football field. Those are like really actually quite macroscopic waves, as opposed to X-rays, which are much closer to the size of a hydrogen atom, and then gamma rays are smaller than a hydrogen atom. Okay. There's a associated thing with this, which is called the frequency. So how often something is passing by. I like to think of frequency as if I'm standing on a beach, right? And I'm sitting there, Corona in hand, and the waves are coming up. And maybe it's like, I'm sitting there for a couple hours and I'm really bored. So I count how many waves came by me and left, right? In, out, in, out. That would be your frequency, okay? So you can figure out how many happened in an hour, and that's the number per unit time. Does that make sense? These are inversely related to one another. So if I have a long wavelength, okay, over here, large, then this is going to be smaller compared to if I have a short wavelength. See these numbers, very small, with very big frequencies. Okay, so there's an opposite to it. Okay. They're also associated with energy. So if I normalize this to 1, we can do fractions. On this side, less energetic. On this side, more energetic. And you'll notice that these are log scale. So this is 10 times more energetic, 100, 1,000, 10,000, so on and so forth. And suddenly it becomes a little more obvious why you shouldn't hang out in front of an X-ray machine. So here's an X-ray machine. They're about 10,000 times more energetic than visible light. Right? So you can have them for a little bit for your phones or your teeth or whatever, but they put on like a lead, what's the thing called? Like a lead bib, so that you don't get any excess. And then the guy who's doing it like runs in the next room. You know it's real safe when they don't even want to be in there with you. And on this side, you have a lot less energy. So for example, you've never gotten a sunburn from being too close to someone. That's really good, right? So here in the infrared, I'm giving off heat, but it's not very energetic heat, right? Whereas way down here, this is quite energetic. That make sense?
Yes.
Okay, so let's think about some practical applications. I've given you some of them before. What are some applications for radio waves? Oh, radio, very good. Anything else? What other technology uses radio waves? Okay, so you're right that telescope will look at all of these, but what technology that we use? Yeah. Radar, yes, radar will use radio waves. Your phone actually is using radar, or sometimes in the microwave. Yeah, so cell phone towers, for example, are sending information via radio waves. Anything else? Walkie-talkies, I don't, maybe. It's in that region. I'm mostly thinking of Wi-Fi. Wi-Fi is and Bluetooth are this part of the wavelength spectrum. Oh, I didn't do all. Satellites? Yes, satellites, you shoot them up and down with radar. And in fact, we get data from other spacecraft at, say, Mars, for example. They send it back through radio waves. We have these huge radio dishes, and you collect it, very faint signals. Say, oh, I can hear you. Right? What are microwaves used for? Burritos, right? Frozen burritos. Or maybe you prefer taquitos, whichever one is fine. What's infrared used for? Example of infrared light?
Oh,
Heat.
spies.
Spies, yeah, like night vision goggles. We got in 007 or whatever it is, Call of Duty, yeah, whatever the kids play these days. Visible. Anyone ever use that? Yeah, our eyeballs are the best detectors, right? They're pretty cool. They can do something called high dynamic resolution, where you look at something that's very bright and something that's very dim in the background. You combine those images with your brain processor. Sick. Ultraviolet, what do we use that for? Tanning bed?
Oh,
Tanning beds are giant tubes. They just fry your outside a little bit, you know, you look a little brown. Or a lot, yeah. Yeah, you can also use them for plants indoors, that's true too, so hothouses. X-rays, we already talked about that a little bit. That looks inside your body, make sure that there's no cavities. What are gamma rays used for? There is no such thing, but I like your enthusiasm. What was that?
Radiation.
Yeah, so we can use them as radiation sources. They mostly come from radioactive elements. So yeah, like cesium. You find like a capsule of cesium-137, don't pick it up. Okay. Anytime that you're in a building, a science building, and you see a little radiation symbol, walk away. Okay. Don't pick things up that say radioactive on them. That's a best rule of practice. Okay. Anything else I missed here? No. Okay, and then astronomically, we also see all of these sources and we will observe them with our telescopes. So for example, galaxies will emit fully in the radio. We'll talk about something called the cosmic microwave background, which is the leftover light from the Big Bang. You'll see that planets and star-forming clouds are visible in the infrared, and we'll see this when we look at J. Davis T images. The sun obviously peaks in the visible. That's really convenient, right? Who would have thunk? The visible part that we can see is exactly the same place where the sun is. That's crazy. What a coincidence. What? Okay, so the sun emits most of its light in the visible, and coincidentally, that's what we see.
Or maybe it's.
Oh, maybe it's the other Earth. So who thinks it's a coincidence? Yeah, I'm gonna trick a single person. Okay, so the sun's chromosphere is in the ultraviolet, really bright lights, and we can see that when maybe we'll get to some cool pictures from Soho. And once you get to really high energy, you start to get things like X-rays from black hole accretion disks, where stars are dying and they're just being violently ripped apart with a lot of excess energy. Or things called gamma ray bursts, which are as cool as they sound. High energy astrophysical sources. So light is a wave. That's how we're going to talk about it today. And we're going to talk about the different components. If you've heard this already, feel free to just check out. The way we're going to talk about different parts of it is that the wavelength is the distance between adjacent peaks, or conversely, between adjacent troughs. So this would be the wavelength, or this would be the wavelength. So pick any point along the curve, and whenever we get back to it, that's the wavelength. Okay? It's not this, right? That's a half wavelength. You're going in a different direction. Okay? The frequency, like we mentioned, is how many crests we see in a unit of time. So if you see 20 waves in a minute, that's a high frequency. If you see 5 waves in a minute, that's a low frequency comparatively, right? Okay. All light, interestingly enough, travels at exactly the same speed. What is that called? The speed of light. Okay. Interestingly enough, radio waves, visible light, none of it has a different speed. And that's why we had this nice inverse thing between the between the frequency and the wavelength. So stuff that was low frequency had stuff that was low frequency had high wavelengths, and similarly stuff that had short wavelengths was, oh my god, I did this backwards. Low frequency. Yeah, okay, that's right. Whatever the opposites of them are. Did I do backwards?
I'm dyslexic, you can't just
Okay, hold on. Let's put it up. Let's put it up. Okay, let's see it here. Let's see it here.
What?
Here's the wavelength, and here's the frequency. So if they are large wavelengths, then it's low frequency. And if they are large frequency, then it's short wavelengths. Because that'll mess me up too, right? This is why we have reference material. Never trust the words that I say unless I have something that shows what I'm saying. Okay? Okay, everyone agree? All right.
Aliens are real.
Oh, it's never aliens. That's the only thing you have to walk away from this class at.
You don't have a slide for that though.
Okay, no, I have a whole lecture on that. So how are the wavelength and frequency of light related? Is it A, if wavelength increases, so does frequency, a direct relationship? Is it B, if wavelength increases, frequency decreases, an inverse relationship? Is it C, it depends on the speed of the light wave? D, it depends on what type of light you're using, for example, X-rays versus ultraviolet versus radio waves, or E, they are not related. Let me know when you're ready to vote. Vote on 3, 2, 1. Didn't get anyone? Didn't trick a single person? Someone want to tell us what it is? B. Why? Nope, you have to explain now. You spoke. You tell us why.
You just heard like a minute ago.
That's like fair. So in fact, we can write it like this. So the wavelength of the light times the frequency is what we define as the speed. So for example, I'm driving my car. I need to get home. I drive about 50 miles away, and I get there in about an hour. What have I just described? Well,
Anything else?
slow.
How long it takes you to get home to 50 miles?
And that's a average speed. So by definition, a speed is the distance it took divided by how long it was to get there, right? But frequency is the opposite. It's 1 over time. So I'm multiplying here the distance divided by how long it took. Does that make sense? Okay. And it just so happens that this thing is a constant for all waves of light. So you can write it like this, you can write it like that. I don't care. Okay, but they're inverse relationships. Okay, interestingly enough, the energy is proportional to the frequency. So the shorter the wavelength, the more energy you get. Somebody's like, what? Think about it this way. If you're sitting on that beach and you know the waves are coming in and you get 5 per hour. Imagine if each one of those waves is bringing with it, say, momentum or energy. Okay, which is going to deliver more energy? Is it the one that you had 5 per hour or 20 per hour? 20. Sitting on the beach, if you saw 20 waves, you're like, oh my god, the ocean's going crazy, right? Right or no? Okay, that's an experience we all have. Anyone not been to the beach? Okay, should have said that in the opposite order. Okay, so therefore we know that gamma rays, X-rays, and UV are more dangerous than visible, infrared, or radio. So when compared to red light, blue light is A, longer wavelength, B, higher frequency, C, lower energy photons, D, faster photons, E, none of the above. Let's vote on 3, 2, 1. Okay, okay. Okay, so when compared to red light, blue light is, anyone want to argue for their choice? Yeah,
Be higher frequency.
why is it higher frequency?
Violet is the most frequent, and then red is the least frequent, and blue is supposed to be light.
Okay, so if we're thinking about it in the context of ultraviolet and infrared, right? We just said that the ultraviolet light has higher frequency. So that's a great analogy, right? Closer to violet, higher wavelength, higher frequency. And in fact, that's true. So here's blue, right? And then the frequency on this side is larger than the frequency on this side. Okay. Everyone getting it okay? Anyone lost? Okay. Infrared light has a long wavelength and a low frequency. How does ultraviolet light, which has a high frequency, compare in wavelength? Does UV light have a shorter wavelength than IR? Does UV light have the same wavelength? UV light have a longer wavelength? Or you cannot determine it based on this information? Let's vote on 3, 2, 1. Yeah, also didn't get, I think I might have gone one person. Didn't want to defend their answer. It's just glitch. They don't want to defend their answer. No. Everyone hates defending their answer, right? That's the worst part of the class. I don't like talking, Mateo. Okay, so this one, UV light has a shorter wavelength than IR light, compared to UV light has a longer wavelength than IR light. No one liked that, and no one liked this. So it's a 50-50. And if I go back one, I'll see that the ultraviolet light here, these, even though it's 10 to the 8th, it's 10 to the -8. So you might need your, what do they call them? Binoculars in order to see that good. But this is a much smaller number than this one is. So the wavelength of ultraviolet light is much smaller than the wavelength of infrared light. And we'll talk about why that's really important when we begin to think about absorption. So for example, the visible light here, about the size of a bacteria. And in general, this means that in order to absorb that type of light, you have to be about that size. So that's a rule of thumb, don't quote me on that. But over here, proteins are very sensitive to ultraviolet light. And so, for example, the DNA in your skin is a type of bunch of protein, and it gets damaged, right? Because it's really good at absorbing ultraviolet light and then becoming cancer. That's skin cancer. Whereas over here, the way that microwaves work is they're close to the size of the resonant frequency in water. And so they start moving around and they heat up the inside of the water. Makes sense? All right. Oh, I already should. No one memorized that, right?
Yeah. Photographic.
Okay, well then let's just put it up here. So these are the ways that light can interact with matter, and we're gonna go through them in some detail that we can think about when we see a picture, for example, of a planet. How are we getting that light? And what does it mean? So there's some words up here. What's the first word? Emission. Emission. What does that mean? Right. Stuff coming off from the object itself, right? So created by the object, given away. Okay. What am I emitting right now? Heat, infrared, right? Heat too, that's another way of saying it, but infrared. What's the second one? Absorption. Absorption. What process is absorption?
Like taking it in.
Take in the heat. Okay. Transmission, what does that mean?
To switch.
Not quite.
Trading.
Transmission in a car, I like that. That's not what we're talking about. Any examples of transmission in this room?
Like a transmission of radio waves,
What does that mean then?
in my head, it kind of sounds like transfer.
Yeah, transmission sounds a lot like transfer. And in fact, when we talk about transmission, that's passing through something. Are there any examples in this room, say, of visible light transmitting? So that would be a form of emission coming out of the bulb, going through your cup. Yeah, that's interesting because what's in your cup? Water and glass. So there is a material substance that she's holding on to, right? And in fact, we can see through that material substance. That's amazing, right? Oh, maybe that's why I'm standing next to this giant thing, right? I can see through it. That's the transmission of light through this type of material. So despite the fact that it's hard, right? So maybe I should put it. Any other examples other than say glass and this piece of plastic? The water, you can see through the water. That's very good.
No window.
Your eyeballs are what part of your eyeball?
Like lens, like the.
There's a lens. Yeah, if you have a lens, your brain, your body makes a lens. Any other thing? There's a major one. We're all
The window.
What's that?
The window.
Imagine there's no window. Imagine.
Oh,
What's-
air.
There you go. It's the one I'm walking through right now. It's the one that the light is passing from there to the screen and transmitting through the air, right? Last one. Anyone familiar with reflection?
Air. Song from the.
Okay, that one's the easiest, right? Which one of these is the easiest to understand? Reflection. Okay, so matter releasing energy as light is the process of emission. Absorption is matter being taken from light. Transmission is matter allowing light to pass through it. And oh, I guess I didn't put reflection on there.
It's because it's the heat.
Yes. So let me ask you a separate question. We're gonna get our brains thinking. Because transmission may be a little weird, right? If I put a spectrum on the front of the room, right? If I put a red filter into the beam here, okay? What happens to the light? Is it A? Okay, so I put a filter, right? Right here. And I want to see what happens afterwards. Put a filter. Here. A red filter. Does blue get through and the other colors disappear? Does red get through and the other colors disappear? Do all the colors turn red? Does red stay red but the rest turn white? Or does it depend on which side of the grating I put the filter? When you're ready to vote. Vote on 3, 2, 1. Okay, we got a little variety here. No, kind of. You don't want to defend their vote?
Wouldn't it be A?
Okay.
Because I think of like the ocean, like what if you go down a certain depth, red is it?
Mhm.
And so I think that would get.
So that is a type of filter called Rayleigh scattering, but it's not the type of filter that we use like in class. It's a physical filter.
I'm thinking of like a stoplight. So a stoplight, I feel, has those filters with blue, yellow, green, not with red, yellow, green, sorry. And then it shines white light from the back of it, of course, and then the red filter makes it red. So that
What do you mean? What do you mean makes it red?
well, it absorbs every other color but red.
Right. So that's the idea of transmission when we think about a specific color being transmitted. So if, for example, I put a filter right here, the reason that everything looks red when you look through a red filter is because the only light that's getting to you is red. Everything else is being absorbed in the material, just like this here does not transmit any light, or at least any visible light. I can't see through my desk. But this is a material which is partially opaque, right? You can see through it, except for these like blue lines and everything else on here. Does that make sense? Okay. Oh, there's the reflection. Yay. The reflection is a way of taking light. And I'm not going to change the properties at all. I'm just going to make it come back from where it came. Okay. Interestingly enough, reflection has a lot to do with smoothness. So when we were talking about like, how do you know it's icy? Right? We had these icy moons. We were like, oh yeah, it looks soft, right? Because it's really smooth. So for example, this is an MC Escher painting where he's drawn himself holding up a metal ball. And of course, this looks really smooth. So if you take, for example, a very nice car, it can be great paint job, you're reflected, right? Smooth surface. Whereas this, I can't use this very well as a mirror. You can kind of see, but not really well. That intuitive, at least anyone? Everyone already knows this. Okay. So why is this strawberry red? Yeah.
Absorbs all color but red.
It absorbs all colors but red. Why is your shirt black? It's not absorbing any colors preferentially. Are all blacks the same?
I thought black absorbed all.
Yeah, we say that generally, but in fact, I can still see this, right? So it's uniformly absorbing all light, but it's not reflecting as much light as, say, the walls are. The walls are doing a much better job at reflecting light than this is. That make sense? Okay. Let me ask you a different question. Does blue light have red light in it?
Yes.
Raise your hand for yes. Raise your hand for no. Does white light have blue light in it?
Yes.
Yes, okay, that one we like. But actually red and blue are distinct. So for example, if I use a filter, like a blue filter, and I get rid of all of the light but blue, and then I use a red filter, what do I see on the other side? What's that? Purple. Purple. Interesting. Do I see purple?
Everything's about blue and then you do red in front of that.
No, so let's say, okay, let me draw the picture. Okay, so here I have white light. I'm gonna use my flashlight. Okay. And then here I have a blue filter. And then after that, I have a red filter. Then I have my eyeball. It's my eyeball. So what color do I see? You still see the red?
Nothing.
See nothing?
See green.
Green? Okay, green, any other colors? I had an early vote for purple. So what happens at this first one?
Only the blue
Only the blue what?
makes it transmit.
Okay, only the blue goes through. So now I only have blue, and what happens at the red filter? Okay. So does any light get through here? No. Because what you're left with is blue. And this red filter gets rid of everything. So if I use both of them, they can start. Now, if you've ever done this with cheap filters that you bought at Costco, then you're just looking at cheapness, right? It's not fully absorbing the red, it's still letting some white light through. Let me ask you a different question. Ready? Maybe a tricky one. What color would a pure red object, like a strawberry that we just saw, be if we shined only blue light on it? Is it A, red, B, blue, C, purple, D, white, E, black? Let's vote on 3, 2, 1. Okay, we got a little variety. Why don't you turn to your neighbor and ask them what they got?
Yeah, I like So, she needed it, and then I have to speak it out. So like, oh, I typed the wrong picture, but like, and they couldn't see what happened. I like those. No.
Okay, what do you think? Is everyone ready to revote? Okay, let's revote on 3, 2, 1. Some people got other people to be convinced. Anyone want to defend their answer?
I've watched a lot of. Yeah, I
Any
was.
TikToks? Okay, so this is tricky, right? Because painting, when I think about something being painted, what process is that? Is that
I was talking about, there's these videos where they paint under a red
Yeah,
light,
that's what.
and you can't see the colors well, and then they turn the light back to white, and you get to see how funky it
And
looks.
like, so
When you
usually
usually
it's
it's
like.
like colors.
They
okay,
have,
right?
like,
So there's two processes there. It's-
This is black, and then like they turn black and purple.
Wait, so go back one second. So you put on the purple,
Or
Pick up
red
purple.
light.
you go to purple and it said it looks black.
Well,
Why did it look black?
that's only red
Everything was
light.
being absorbed in the same way this was, right? So think about it this way. So this object, instead of being a filter, let's imagine it's a strawberry. And we said that the color of the strawberry is only due to the fact that it's absorbing all the other types of light and reflecting the red. So that's almost like this. So if I only give it blue, then it absorbs all the blue and reflects nothing. And we said that the absence of light is kind of weird, right? So let's say you take some strawberries and you bring them to a new solar system. Okay, but that solar system peaks way in the infrared. Now all your fruits and vegetables, they're all gonna be black. Crazy, right? And you go visit, so we always watch these like movies, like Interstellar, whatever, they go to some new solar system, they land like in Andor, and they look around and they can see everything. But our eyes only see a very small portion of the wavelength spectrum. So the most likely outcome is that you would go somewhere and everything would look gray and white. Well, no, there's still light, but it just be in grayscale. It's very creepy. So you want to do science fiction, right? Talk to me.
Like.
Okay. What? Say that again? Twilight Zone? I never watched that. We're not gonna go into this. We don't have time. We don't have time. Okay, so what color are hot objects?
Red.
Yeah. I don't know. I'm asking. What color are hot objects?
Almost
Red.
purple.
Okay, raise your hand for red. Raise your hand for blue. Why is blue hotter than red? That's not what my shower says. My shower says if I turn the red one, I'm gonna have a bad morning. If I turn the blue one, it's also a bad morning, but for different reasons. You want both, right? And yet we have it flipped in our brains. So we think of blue as like ice, like fresh water, and red is like fire, but that's wrong. So in fact, there's a process, okay? Let's take an iron poker, and I'm having a really nice campfire with my friends, and the only thing I do is instead of talking to them, I just play with the logs, because I want to make the fire bigger. And so I start off with a black iron poker. It's made of wrought iron. And as soon as it starts to get warm, it starts to glow a little red. And maybe I made a really good fire. So now it's getting really hot, and it starts to get white. And if I keep stoking the fire, maybe I pour some kerosene on there or something, I can get it up to blue. And then it starts melting. Right? No. Okay. All right. So this is the counterintuitive way that we want to think about heat, about temperature, and about light. Okay. So if I show you a blue star, for example, you know that that's hotter than a red star. Does that make sense? Okay. So we need to get one of these. I want to buy one of these for the classroom, but you can get an infrared camera. You just set it up in the back and then you walk around and you can see, okay, this is an infrared image. And what's that? Yeah, that's a very good question. What is he holding? It's a match. So this is a light. Why is this the worst color scheme? Because red is hot here. Okay, so what are these? His glasses. I hope his eyes don't look that big. So in fact, he's wearing sunglasses here, and the sunglasses are reflecting infrared light. They are not letting infrared light in. So they're cooler. What's the coolest part of his face? His nose, right there. And then maybe his open mouth. Okay. No, I'm just saying there might be a tie between these two. Okay. Does process make sense?
Yeah.
Okay. So we're going to talk about a couple different types of spectra in this class in order to do the lab for today. And basically we've talked about the process of being absorbed, of being emitted, of being reflected, and of being transmitted. And so now we're going to think about, say, material when observed through different configurations. So imagine I have a hot light, right, over here. It's a lamp. And then I have the prism. And the prism is giving me the rainbow. Perfect, right? So what's actually happening here is that hot things here emit a little bit of light at every wavelength. Okay. This is sometimes called black body radiation. And what we're looking for when we talk about something like this is where's the peak? So when we look at the sun, for example, it just peaks right here in the visible. But for example, a cooler star, 3,000 degrees, as opposed to our sun's 5,800, that peak is going to move towards the right, towards the infrared. It's going to peak more in the red. Okay? As opposed to a really hot star, like a 15,000 degree star, that's going to be over here in the blue. Okay. Now you'll notice a couple things about those curves. None of those lines intersect. Oh, kind of cool. We didn't see that before, right? So there is no point on this curve. This curve only goes up and to the left, up and to the left. So for example, here you're down here, 310 degree Kelvin. I should say Kelvin, not degrees, sorry. And you peak in the infrared. You don't really produce any visible light. That's good. And you definitely don't produce any X-rays. Right? That'd be very dangerous. And this shape, as it moves over and to the left, is telling us that there is a direct relationship between the temperature you are and the color of the peak. Right, we kind of already said that, but now we have a formula for it. This is called Wien's law. Okay. Comes from quantum mechanics, but we're going to just use this here, which is that the peak of the emission is inversely related to the temperature. You can flip this around, you can do the peak of the frequency of the emission would be directly proportional, but we're not going to do that because that's probably intuitive. Okay, so let's go back to the question of why do we see indivisible?
Humans evolved so that our light sensors can pick the objects around us with the wavelengths of light that peak from the sun that we experience.
So we evolved with access to this, and the most information that we have is right here. Right, so before we made all these lamps and cool other things, we just had to wake up and see the sun. Right, we had to navigate that way. Okay. Cave, you ever see these like cave fish that have fully evolved in caves? What are they missing? Eyes. They don't have eyes. They have no need for them. They get around with no eyes. Don't say you. You don't know. I didn't show you a picture.
They just,
Well, what do they do in the water? They just swim.
they don't like,
Yeah, so they have something called the amphiloblorenzine, which allows them to detect electromagnetic waves in the water, so they can see when other fish and other things are happening. They will feel pressure. They have like pressure all over their skins, and they can also feel each other. So sharks use these to navigate large distances. Sharks have these as well, and they'll align with Earth's magnetic field in order to know which direction they're going in the ocean. If you've ever wondered how sharks navigate over thousands of kilometers. Okay, so we do what we have access to, right? If you look at, say, the evolution of stuff at the seafloor, it's going to look different than what we have access to. Okay, so let's use all these concepts. This one's tricky. All right. 3 spectral curves shown in the graphs below illustrate the total energy output over the whole surface versus wavelength for 3 unknown objects. Which of the objects has the highest temperature? Have a look here. If it's hard to see, let me know, and we can turn the lights off here. Let me know when you're ready to vote. Let's vote on 3, 2, 1. Oh, okay. Almost everyone has a different answer. I'm going to turn to your neighbor and see if you can convince them of your answer.
Okay. Yeah.
but these chickens.
Okay, yes.
Is that a letter?
Yeah, that's the word UV. That's VIBGYO. B is blue. V is at violet. I is at indigo. Sorry, I should maybe write those underneath. Okay, we ready to revote? Let's revote on 3, 2, 1. Yeah, I got rid of most of the C's, but now it's almost evenly split between A and B. How are we gonna solve this puzzle?
I think because it starts, the dotted line starts right before violet.
Oh, okay, so it went here.
Yeah.
Okay, you didn't care about how tall it was? Why not?
I think it's the coverage, like. coverage.
Right, so in fact, we said that the peak temperature is inversely related to the wavelength. So for example, we have to go back a few seconds because we're learning all these concepts at once. Ultraviolet waves are very short. Okay, that means the temperature to produce them is high. So if we go back one more here, we see that is true. As I move to the left-hand side, okay, here's wavelength. Okay, as it gets smaller, the temperature is going up. As it gets bigger, the temperature is going down. So what I'm looking for here is not the tallness, right? Because I tricked you. It says total energy output. It says the energy output over the whole surface. I didn't tell you how big the surface was. So if I make a larger surface at a lower temperature, like peaking in the green, then I can make this. As opposed to this, maybe is a very hot surface, but just like the size of the desk, right? The total energy is low, right? Did it feel like a trick? Right on the thing. Okay, so in practice, we're going to use all of these processes to understand the atmospheres and the surfaces of planets. So we're talking about this in the context of light as giving us information. Okay. So here we're going to measure how bright a light is at each of its different wavelengths. So we've used something akin to a prism, and we're going to separate it by its components and look for where it's bright or dark. And the brightness and darkness is going to tell us something about the surface. We can determine the composition, just like you're scanning something at self-checkout at Target. Or you can determine the temperature in a way we just said, right? By looking at the peak of the emission. And then we can talk about the velocity. That one's crazy. We'll talk about that. Okay. What's this object? Yeah, but what's the spectra of? No, why not? Too low?
Like, the wavelengths like.
We're gonna actually do this one. This will be a homework problem, but there's a reason why it's not the sun.
Isn't the sun just like overall, like for the most part, not going in the down?
Yeah, there's not a second peak in the sun. So notice here you have one object like that. That would be the sun, and it peaks in the visible, and there's no secondary peak. Okay, these all look like a little hump. So the fact that there's two peaks here tells us something very unique and very interesting. We'll talk about it in a second. Oh, no.
Wait.
Very started.
Stop. No more guessing. We're gonna learn. Okay. Yeah, question back.
Yeah, I was just gonna say it feels like a planet transiting from stars.
Okay, that could be a thought. So two different objects here,
Black.
but it's not. Okay. So there are three types of spectra here that we're gonna talk about. So if we look at the different features that we saw spiky bits, we saw big bits, and we saw spiky down bits. Okay, so that is a combination of an emission line spectrum, which we are going to make today with our lamps. We have a continuous spectrum, which is kind of what we're getting with the fluorescence, but not quite. And then we're going to have an absorption line spectrum. And that's what we started off the class with. It's the solar surface. Okay. So in order to do that, we have to quickly talk about atoms. Who's taking quantum mechanics? Okay, good. So we're all in the same boat here. So in fact, quantum mechanics is a weird world. So if I want to go up a hill, I just walk up the hill and I can stand on any place on the hill, right? And as I run down the hill, or if I roll down in a barrel, right, I can go whatever speed I want. Right, that just roll all the way down. But in a computation, in a quantum mechanical world, I'm only allowed to stand on certain levels. That's why it's called quantized. Quantum just means a single parcel. So for example, I have a different energy if I sit on this versus if I stand or if I sit on the floor, right? But in a quantum mechanical world, I would not be able to exist halfway between the floor and the ground. Only sit on the ground or only sit on the floor. Okay. Yes or no?
So there's no middle.
There's no middle.
Okay.
There's just little steps. So think about, for example, energy as being in steps, just like the stairs as you go up and down a house. Right? Okay. Okay. No. So we can think about atoms this way. Okay. And they basically have two components. They have a proton or neutrons in the middle, we call it the nucleus. That's the positively charged part. Then we have an electron, that's the negatively charged part, and they are attracted to one another. They do not end up smashing into each other because they're not allowed to. Okay, they're only allowed to live on these exact what are they called? Steps, right? And there's a base step, okay, and that's called the ground floor of the atom itself. But the things you want to keep in mind here, hydrogen is simple because it has one proton and one electron. Its net charge is 0 because this is +1 and that's -1, so that's a net of 0. Here in oxygen, I have 1, 2, 3, 4, 5, 6, 7, 8 electrons. How many protons do I have in here? Probably 8. Probably 8, sometimes less. Okay. And molecules are just when this stuff likes to hang out together. So if I put hydrogen and oxygen close to each other in the right temperature conditions, the right pressure conditions, they'll be like, hey, do you want to like share some electrons? And then the hydrogen will be like, yeah, I love it. And oxygen is like, yeah, cool. And so then oxygen in the middle is sharing with 2 hydrogens. Okay? Okay. But every atom has different energy levels. So I told you that just like scanning at Target, you have these individual lines that tell you that it's like the cereal you just bought, for example. No 2 people have the same fingerprints. No 2 elements have the same emission spectrum. So the different stairs, so to speak, in an atom are at different sizes. So some stairs are really close, some are really big, because we said earlier that this is high or low energy on this side. High energies, and this is low energy. So we are directly looking at the energy of each step. This step here must be a big fall because it's a high energy step compared to this one here, which is like a tiny little step. Okay. So not only do I see that in this spectrum, I also see that carbon is a lot less interesting than neon. Neon has all of these lines in here. It has all of these steps that electrons can go up and down, whereas carbon only has a few. And we'll see hydrogen today got a couple, very boring. Okay, no one likes it. Magnesium is the best, because I do my research on that. Okay, so here's hydrogen. There's one there, a couple over here, boring. Here's sodium. Oh, sodium's crazy, right? In fact, sodium is great because there is only a couple lights or a couple steps that exist in the visible spectrum. So we love to, if we can, use these lights around observatories, because then they're not adding any additional light into our observation. So as you drive up the observatory, you'll notice there are all these weird orange colors. That's this, sodium doublet. There. You can see 2 of them right next to each other. So this is one step that actually gets split by a quantum mechanical effect. It's weird. I told you, but don't listen to it. Okay, here's helium. Helium's a weird one. Where was helium first found? What's that? No, what does this part of the word look like? Helios, which is the sun. Helium was first found in the sun before it was found on Earth. Crazy. So we knew about hydrogen. We had lots of hydrogen that comes off the water, but helium is an inert gas. It doesn't like to play chemistry. It just loves to leave. So it just bubbles up to the top of the atmosphere and it gets the fuck out of Dodge. It's an introvert, yeah. It doesn't like to exist. So we looked up at the sun and we said, there's all these weird lines that must belong to someone because they could account for most of the other things. Like, this is such a weird atom. And then it's helium. And then, of course, we make helium either by getting it from underground reservoirs, from nuclear reactions in the core, or we do nuclear reactions here on Earth, get some free helium, right? Maybe one of those, like a little, you set up a little nuclear bomb and you get a little, you know what I'm saying? No. Okay, good. Neon, really fascinatingly, has anyone seen a neon light? What color is it? No, it doesn't depend. If it's not this red orange, it's not neon. So what they do instead is they put other gases in there. And you can tweak the color of the gas. You can add some xenon, you can add some mercury. As long as it's in a gas form, it's not too dangerous, but definitely don't breathe that gas in. Okay. So if you've seen a green neon light, it's not a neon light. Sorry. Okay. The colors that we see in astronomical objects tend to show us what the object is. So for example, we can look at the Crab Nebula, and we can imagine we grab some piece here, and we put that piece of light through a spectrum, and it ends up looking like this. And because we just looked back here, I didn't include an oxygen. Moron. Okay, there are lines of oxygen emission that happen to line up, right? Exactly where you see these spikes. And you say, oh, that's easy. There's doubly ionized oxygen. That's what's making this really bright. Oh, interesting question. What color is this? What's that? It's more red, right? Compared to over here, which is shorter wavelength and therefore more blue, right? So here I have some singly ionized oxygen in the blue, and over here it's red, right? What about this one right here? Maybe greenish. Oh, I can understand this picture now. This green in here is hydrogen. The red is oxygen. The blue in the middle is doubly ionized oxygen. And that means when something's doubly ionized, you use a lot of energy to remove 2 ions. So if I removed 2 ions, it must be really hot. Look where that is. That's in the middle where the explosion just happened. Well, there's one over here too. Sorry, singly ionized. You're right. That was backwards. That was backwards. That was tricky. I just got myself. But there's also red from atomic hydrogen, so it's not a perfect story.
Pretty good one.
It's a pretty good one. As for faking it, that was pretty good. The colors that we see here directly tell us about different elements. And the concentration that we see in this doubly ionized oxygen here can be happening for a number of different reasons. So it could actually be very hot out there, but it might be because it's shock heating. Yeah. So when material runs into other material, it heats up. So that's what you call shock heating. So supernova are really cool. This one is the Crab Nebula and was observed in 1054 by, remember we talked about this ancient astronomers like 17 weeks ago? This is the ghost star that they watched happen. Yeah.
What the Chinese?
Yeah, by the Chinese.
In 1054.
In 1054. They kept such detailed accounts that they went and they looked, and then they ran the simulation back. They said, "Oh, it's about 1,000-year-old." that cool?
Nearly a whole millennium has been discovered.
Almost. Almost. Oh, I guess we'll be around for it, some of us. Okay. So that was the first type of spectrum. That's emission spectrum. And it happens because you have some prism here. And you have a gas cloud with electrons that are moving up and down, absorbing and emitting. That's the emission spectrum. So this is giving off light. But atoms can only give off certain types of light. So we saw the oxygen atom, for example, only able to give or receive a certain type of light. Make sense? Did I lose anyone? Okay. So that's that one. We talked about continuous, that was the rainbow. What's the absorption?
It's like low light. It's
Right, so how would I configure that? Yeah, so I have a gas and I have a light.
Those are the gaps.
Yeah, I wanna see an absorption spectrum, what would I have to do?
That's the light that comes out.
Well, if I have a gas cloud, I'm gonna get emission. If I just have a hot gas cloud, I get emission. If I have a light, I'm just looking at the light, I get continuous. So now I wanna mix these somehow to get the absorption.
shine the light on the gas.
Yeah, I wanna subtract those out. How did you do that?
Yeah, you have to trap the gas and then shine white light through it to see where you get on the other side.
Ah, okay, so you start with the light source behind the gas, and then we see what gets absorbed. So we start with the continuous light, like the sun produces continuous light, and then we put an atmosphere on the top of the sun. And that atmosphere has atoms in it. And in fact, it absorbs different amounts of light. So we talked about sodium, that's the sodium doublet right there. And it's in yellow. Okay? I don't know what the rest of them are going is. But there's a lot. Sun hot, okay?
Looks like a brick wall.
Yeah, so what you're supposed to do with this is that you're supposed to grab each one of them, and put them side by side. It's really long, it's really like detailed map. But of course, I don't have the predictor. Like all the way around. Okay. Good, great. So you're right, it's a hot object viewed through a fluid gas. And this allows it to absorb light. And those electrons are gonna jump up, they're gonna use that, and they're gonna take it out of the continuum. Right? So they're going to absorb, they're gonna move up, and then they transmit what wasn't absorbed. So that's why you get these dark lines in bright light. Okay. Okay, we're almost there. Oh, that's it. Whew. Okay. So now we can do the lab for today, which is gonna be. Can we go see if they got printed? I think I sent it to get printed, but otherwise, so the lab we're gonna do today, we're going to use essentially what amounts to a prism. These are diffraction gratings. If you haven't used one before, you're gonna have fun. If you have used one before, you're still gonna have fun. And what you do is you'll notice that as I look through any light source, there's a preferred direction. So the way that it's going to diffract is going to be, if you're holding it like this, it's gonna be this way. So if I look at this light here, nothing will happen. If I look straight through it, I'm gonna look to the side, and it's going to separate. Does that make sense? Okay. Please return them afterwards. They're not cheap. You can start looking around the room. Fun. See what kind of lights you see. Oh.
Where's this glowing?
Okay. Or maybe I'll just go grab it. You know, like. I'll bring it back.
Yeah.
I know you too.
Yeah, and we're like, okay.
That's so crazy.
It's hard for me to look at it. But you can shine a flashlight here? Oh, not like that. What do you like, man? I don't like them, not in rainbow or their faces. Good. Let's see. I see thing nine. What? Tiny rainbow. Go this way. No.
Oh, shit.
You make me cry.
Oh, you're.
Okay, so, stop the muting.